Now see this example. In this example, it is given a tight wound long solenoid having 50 turns per centimeter and it carries a current of 4 ampere. Find the magnetic intensity H and magnetic field B at the center of a solenoid. And again they are asking what will be the values if an iron core is inserted in the solenoid and the magnetization in the core is this much. It means what is given here, this is the solenoid and current in the solenoid is I given. So first they are asking the B value. So directly we can get B is equal to your mu naught N into I. N is the number of turns per unit length, and so the value of mu naught is your 4 pi 10 power minus 7, and now N, number of turns per centimeter here 50 into 10 power minus 2, and I is the current given here 4. So now we can get here magnetic field inside the solenoid can be given by this relation B is equal to your mu naught N into I. So where mu naught is your 4 pi into 10 power minus 7, N is the number of turns per centimeter, that is given your 50, the 50 per centimeter, so that can be converted into meter 10 to power 2, and then I is the current given here 4 ampere. And now we can simplify. So B is equal to here, we can check it here, 4 pi 10 to the minus 7, 15 to 4, 200. So 200 into 10 power minus 5. So then we can solve 8 pi into 10 power minus 3 Tesla. This is the value of B. Now then they are asking H. As H has been defined as B by mu naught, so which is nothing, B by mu naught means N into I, and the value of N is your 50 into 4, so this become your 2 into 10 to the power 4. This is the value of H. This is the answer of first part of the problem. In second case they are saying an iron core, and core is now here. In the second case an iron core has been kept inside the solenoid, due to that some magnetization will be there. So in that case B is equal to, B has been defined here mu naught H plus I. This is the value of B. So we can get the value of B mu naught H plus I. H value will remain your same. H is nothing, H is the magnetizing power here. The B is equal to your mu naught value your 4 pi 10 power minus 7, and H value 2 into 10 to the power 4. I is the intensity of magnetization, that is your 4 into 10 power 6, 4 into 10 power 6. So this is your 402, 4 pi into 10 power minus 7 into 402 to 10 power 4. So approximately we can say 4 pi into 402, this is your 4.02. So 4 pi into 4 into 10 power minus 1, 16 pi or around 1.6 pi. This is the value of B Tesla around. So this is the one of the problem. Now see another problem. So now one question is given as find the magnetization I, the magnetic intensity H and the magnetic field B at the center of a bar magnet of pole strength 3.6 ampere meter, magnetic length is given 12 centimeter and area of cross section is given 0.9 centimeter square. So see the how to solve this one. Meaning of that, this, let this be your magnet and poles are at the one of the ends and this is the length total given, pole strength your M. So first thing they are asking the magnetization I and magnetic intensity H, all these values they are asking at the center of this. So see, at the center, if when we are looking here, so at the center magnetic field due to the positive and negative, see, so B is equal to here mu naught by 4 pi M by R square. R is the, you can say, distance from the center to one of the pole, that your R square, and here one is your positive, another your negative dipole. So due to negative towards this, positive this, so net magnetic field your it become your 2 times. This is the value of B. So now we can calculate here mu naught by 4 pi 10 power minus 7. M is, M value given here, pole strength 3.6 into 2 by R square. R is your here L by 2. L is here length of the 12 centimeter, that is 6 centimeter, 6 into 10 power minus 2 whole square. Now we can simplify this. 10 power minus 7 into 7.2 by 36 into 10 power minus 4. So B value will come here 10 power minus 3 into 0.2, so which is equal to 2 into 10 power minus 4 Tesla. This is the value of B. Now when H they are asking, so this is the answer of, you can say, the C part. Now B part, as we know H is equal to your B by mu naught, so we can solve the value. B is your 2 10 power minus 4 and mu naught value your 4 pi into 10 power minus 7. So this will be your 1 by 2 pi into 10 power 3. This is the value of H. Now intensity of magnetization first. I, as we know, intensity of magnetization means magnetic moment per unit volume. The magnetic moment, your magnetic dipole moment, that is your M into L, and volume here your area of cross section into L. So M by A, M is the pole strength which is given 3.6 and area of cross section given here 0.9, 0.9 centimeter square 10 power minus 4. So this will be your 4 into 10 to the power 4 and ampere per meter. This is the value of I, intensity of magnetization. So this is the another example. Now see one more example. Now it is given as a toroid has a mean radius 20 by pi centimeter and total number of turns in the toroid are 400, carrying current 2 ampere. An aluminum ring of at temperature 200 Kelvin, 280 Kelvin inside the toroid provides the core if intensity of magnetization is this much. Find the susceptibility at temperature 280 as well as if temperature is 320, then what will be the magnetization intensity? See the meaning of this question. First of all, toroid is given. Toroid means this is your you can say aluminum ring. On this aluminum ring, a wire has been wrapped like this. Due to this wire, and in this wire some current I is there, and this is the mean radius of toroid. So I is the current here. So first point here, they are asking susceptibility. In this toroid, induce, or you can say intensity of magnetized. Magnetized field is given here 4.8 into 10 power minus 2 ampere meter. So due to this current, what is the magnetic field on the axis of toroid? So magnetic field on the axis of toroid, is B naught is equal to mu naught Ni, and which is equal to your mu naught n number of turns per unit length n by 2 pi r into I. This is the B naught. So H. So H is equal to your B naught by mu naught, which is your Ni by 2 pi r. So now check it. N value given here 400. Current in the toroid is your 2 ampere, and 2 pi r, 2 into pi, radius of toroid given 20 by pi in centimeter. So in meter it become your minus 2. So from here we can get pi and pi cancel, 2 into 2, 2 and 2 also cancel, 20 into 40, 400. So this is your 20 into 10 power 2. So this is the value of H, and I value here is given here. So susceptibility at temperature 280. So that susceptibility, as we know, is equal to your I by H. So I value here 4.8, 10 power minus 2, and H value your 2 into 10 to the power 3. So this is your 2.4 to 10 power minus 5. This is the susceptibility at temperature, we can say 280. At temperature 280, the susceptibility. This is the answer of first part A. Now for second part, they are asking what is the magnetization at temperature 320. Magnetization means I value they are asking. In I value, H will not change. So see the second part. I is equal to your susceptibility at 320 temperature into H. H does not depend on temperature here. So as we know, relation susceptibility or inversely proportional to temperature. So as susceptibility inversely proportional to temperature T2 by T1. So at 320, this is your susceptibility at temperature 280 by susceptibility at 320, temperature here 320 by 280. So we can write susceptibility at temperature 320 here 28 by 32, and susceptibility at temperature 280. At 280, that value 2.4 10 to the minus 5. Minus 5, and H value, H already we have calculated, that is your 200 into 10 to the power 3. Now simplify intensity of magnetization. 7 by 8, 8 into 0.3, 3 into 2, 0.6, 0.6 into 4, 4.2. 4.2 into 10 to the power minus 2. 4.2 into 10 power minus 2. This is the intensity at this temperature, ampere per meter. This is the one. Another example based on your magnetic properties of material. Now, this is the general idea about magnetic properties of material.